Okay, Jeremy, it's all yours. See you in a little bit.
Okay, thank you so much. And I really appreciate the kind introduction and the award from the society here. It's wonderful to be back kind of in front of you guys. I know we're all looking forward to the point where we get to do this in person again. But we're going to try to have...
Do you want to turn on your camera, or is that not a thing you can do today?
With this computer, unfortunately, I won't be able to do that. I'm sorry about that.
That's okay. Just checking. Sorry.
Okay.
Sorry for the interruption.
No worries. No problem. So like I was saying, we're going to try to have some fun with this tonight as best we can from a virtual perspective. I'm excited I have the opportunity to speak with everyone tonight. So thanks for being here. Today's topic, as mentioned, is EMC testing challenges beyond 40 gigahertz. And I want to give a special shout out to Malcolm. We're covering this because that's where all the spooky things happen as we get close to Halloween. I really like that opening line. So thanks for that. As far as who I am, I know there's probably people out there that aren't familiar with me, although I can't use video. This is what I look like. I think the introduction kind of covered most of the information here, but since we can't clink glasses together, I'll just add a couple more details here. I have done a number of different positions within Roden Schwartz, which I think helps me in my role as the EMC products and systems product manager. I actually started on the sales side with some of our general purpose products. I became an application engineer. Back in 2015 is when I moved over to the marketing side of the company, and I was actually in charge of our mobile network testing portfolio. That's where some of my papers and presentations about interference hunting and direction finding came from. And I actually became the EMC product manager back in 2018. A year later, we decided as a company, we wanted to be part of the ANSI C63 standards committee. I do serve as the primary representative when those meetings are in session. And I can say safely that due to the pandemic, that group has not been able to meet face-to-face in quite a while, but the standards are moving. So that's a good thing. So anyway, just a little bit about me as I talk through the presentation tonight. I truly look forward to meeting you in person whenever that is going to be possible. All right. So as far as what I'm going to talk about tonight, really the way I've organized the presentation is we're going to talk about 4 different industry trends that we're seeing along the theme of the presentation, which again is EMC testing challenges beyond 40 gigahertz. The first of which I'm going to be talking about is how 5G is really everywhere. Certainly by now, everyone has heard of 5G. I'm not going to really go into much detail. I'm going to more focus on relating 5G testing in the EMC world, and especially at the higher frequency end, of course. And then I'm going to move on to how EMC standards are evolving. Realistically, I understand the group I'm talking to, you guys are right in the middle of the heart of the automotive industry. So I'm going to try to weave in as much automotive related stuff that I can. You will also get a lot from the military automotive or the military government side as well. I think in general, a lot of things kind of start on that side of the industry and eventually kind of work their way into the commercial and other testing industries that are out there. And we'll kind of talk about some of that in that section. The third trend we'll talk about is related to cybersecurity and the concerns that are starting to grow quite a bit there. And I'll end with some discussion about IQ record and replay. This is a particular use case that is really exploding right now, and that does include up at the super high frequency stuff. And I'll kind of discuss the testing challenges posed there and keep it very general as far as how you can, tackle those challenges. If you do have questions along the way, I know that we're using Zoom today. There is a chat feature. I've got it up. I will do my best to take a look over there. If I happen to see a question, I might be able to stop and answer it. Otherwise, I'll certainly check at the end of the presentation and try to attend to as many questions as I can. All right, so let's go ahead and jump into the first trend here, which is about 5G. Like I said, I think everybody knows, roughly speaking, what 5G is and what it's all about. But I'm going to try to relate it to EMC here. One of the tests that you must be able to perform is called RSE, stands for Radiated Spurious Emissions. I'll give a more formal definition on the next slide. But the main point I want to lead with right away, since we're talking about challenges beyond 40 gigahertz, is These days, the standards bodies are requiring you to test up to 200 gigahertz. I will actually provide some detail about why that is. But aside from that, 5G is also used in the aerospace and defense industry, and certainly the automotive industry for radar testing. And depending on which industry you're in and which standard you're paying attention to, that can range anywhere from 77 all the way up to 300 gigahertz, certainly well into the millimeter wave band, as you can see in the figure at the bottom. And then, as we kind of zoom in on the aerospace and defense side, I mentioned there's going to be quite a bit of that in today's presentation. If you look at the conducted emissions test, CE 106, we're envisioning that requirements will go up to 100 gigahertz. Don't go out and look at the standard and say, no, Jeremy, that's not in there yet. This is something that we're expecting to happen as we're talking to some of the customers out there. I do believe I have another slide on this in just a little bit that expands on this idea. So main takeaway here is that we must test higher and higher frequencies. This is coming down the pipe. As you look at the industry in general, if you want to take any kind of electronic to market, the reality is that bandwidths are getting wider and frequencies are getting higher, and test setups are getting more and more complex. As far as EMC goes, radiated spurious emissions is the main concern right now when it comes to 5G. So if you're not terribly familiar with RSE, the formal definition, or a more formal definition of RSE, this is a test that's typically performed within a chamber. This is kind of an over-the-air type test. If it's a radiated versus conducted, a radiated type test suggests that you're doing something over the air using an antenna and so on to determine if an intentional radiator is creating energy at harmonics beyond a defined limit line or your emissions. Again, our CE 106 and RE 103 requirements have very similar wording to this that I'll show you in just a moment. There's an example screenshot of what an RSE test might look like. You have the red limit line, and then of course you have the device emissions, which you're hoping everything stays under that limit, of course. Super basic stuff. I'm talking to the EMC community here, but I wanted to make sure I include it because another good Malcolm line here, the spur that goes over the limit line is definitely a trick in this case. Anyway, that second bullet point talks about CE 106 and RE 103. If you look in there, I've actually highlighted the sections which are very much similar to what you see in that first bullet point, talking about testing for harmonics, and you're looking for spurious emissions, a certain amount of dB down from the limit line. RE 103 just straight up calls it radiated, spurious, and harmonic emissions. So this is all over the place. MIL standard, which is what these two tests happen to be inside of, those have been the front runner for many things in industry. The reality for the automotive industry, a point I want to make here is that the end customer is going to be ultimately responsible to make sure that a module meets requirements at a system level. What I mean by that is we know that vehicles are tons and tons of computers and modules, if you will, put together into one large system, aka the vehicle. Even though a single module or single computer type piece of hardware has been tested to the standard, as soon as that's shipped to an end customer and they put it in with several or even hundreds of other modules, it's still up to the individual automotive customer to make sure that the requirements are met as an entire system. So that's something I definitely want to point out here while we're talking about it. So RSE is definitely a concern for the aerospace and defense community just as much as the automotive community. Okay. Some basics about 5G that are kind of pertinent to today's presentation. If you weren't familiar with the specifics, I just want to introduce the two basic frequency ranges that are commonly referred to with 5G. That's frequency range 1, or FR1 for short, and FR2. These are defined by the standards body called 3GPP. FR1 is kind of your typical frequency range. What I mean by typical is that if you look at cellular technologies like 4G, 3G, and so on, everything is sub 6 gigahertz. And we kind of understand the propagation characteristics and the attenuation profiles of how these signals actually propagate over the air. Now, all the really interesting work, at least in my opinion, is at FR2, which certainly gets up into the millimeter wave band, goes from roughly 24 to 53 gigahertz, as you can see on the slide here. And that's certainly something that we're talking about today. The challenge is beyond 40 gigahertz. FR2 lays squarely in that. And if you want to read more about how these requirements are actually set. There's several of them. When it comes to EMC, I'd draw your attention to the first row in that table there about RF test specifications for user equipment and base stations. They will spell out specifically what you need to do for radiated spurious emissions. And just as a sneak preview, I want to tell you roughly what you're going to find in that area of the standard. So there's actually two standards bodies that are concerned with radiated spurious emissions. You have the 3GPP, which we talked about on a prior slide. You also have the FCC. So in general, 3GPP is actually a little less stringent than the FCC. And we can see this in some of the bullet points on the slide here. If I start with 3GPP, to perform radiated spurious emissions, you must test up to the second harmonic. For historical reasons, radiated spurious emission tests have been around for several years now. The limit is always set roughly at -13 dBm using total radiated power method. Both of these standards bodies adopted that, but 3GPP ended up defining that you only have to go up to the second harmonic, whereas the FCC says you must go up to the fifth harmonic. And I want to spend just an extra minute kind of explaining the first bullet point for FCC. When it comes to RSE testing, the actual requirement itself comes down to what the highest frequency your device is capable of emitting. So for example, if I have a device, its highest frequency it can put out is 25 gigahertz. That's less than 30 gigahertz. So I'm in this kind of first scenario. I would need to test from 30 megahertz up to the fifth harmonic or 100 gigahertz, whichever's lower. So if my maximum device frequency was 25 gigahertz, 25 times 5 is 125 gigahertz. In that case, I would take the lower of the two, it'd be 100 gig. Now, alternatively, if my device has a frequency over 30 gigahertz, this is how we would get up to 200. So let's say for a second, my device was 40 gigahertz. That's a bad example because they're equal. 50 gigahertz. 50 times 5 is 250 gigahertz. Again, I would take the lesser of the two. In that case, I would need to test, according to the FCC, from 30 megahertz to 200 gigahertz. And that's where that number came from a couple slides ago. All of this is certainly written out in black and white, like you would find with any EMC standard. A lot of the procedures, according to one of the ANSI C63 standards, C63.26 to be specific. But for today's presentation, I think this is deep enough. As you can see, this is a 5G related RSE test that requires us to go up to 200 gigahertz. And in general, this can be challenging to do because you need a certain amount of sensitivity and dynamic range to get there. We know that the higher in frequency you go, the higher the attenuation. It can be hard for those signals to get where they need to go. So here's kind of a general solution that could be used to address that situation. And I purposely put this back to back with the last slide so that you kind of have in your mind that FCC requirement, especially that goes up to 200 gigahertz or the fifth harmonic, whichever is lower. To meet those sensitivity and dynamic range requirements well, this actually takes a small village, right? So there's several pieces of test equipment that need to work together. The brains of the operation, if you will, is the EMC software. Definitely helps automate some things. And if you need to switch an antenna, for example, some of these receive units and multiplier units we'll talk about in a minute, kind of drives everything. You certainly have a test receiver to look at the emissions themselves. A call box, there's a switching unit, and all this is driven and kind of connected by a signal generator. And the thing that I think is most interesting about this approach, because you have to cover such a wide frequency range, you can break this up into multiple different frequency levels. And what I mean by that is, again, it's based on how high of a frequency that's in your device. So if according to the standard, you only have to test up to 80 gigahertz, you wouldn't want to buy a solution that goes all the way up to 200 gigahertz, unless you wanted to leave room to grow in. But you can actually purchase receive and multiplier units that only go up to 60 gigahertz, and then maybe you could graduate up to 90 gigahertz when it's necessary and follow the same logic until you get up to 200 gigahertz. This is a common way to do this kind of solution when you have to cover such a wide frequency range. Now, when it comes to the automotive community, it's important to note that there are some other pieces of test equipment that are starting to follow a very similar path. One is a radar echo simulator. It has a front end that you can actually change the level at which you want to measure. So you can get higher and higher frequencies, but you kind of pick the break point, if you will. With all of these type of solutions I'm talking about on this slide, the idea is you're not supposed to be running very long cables at these high frequencies. The attenuation is just far too much. So it's really, really important to keep that front end close, you know, to the mixer and not have this long cable to interface with the instrument itself. All right. I also want to touch a little bit more on the test receiver. You can see the LO and IF kind of coming out in here. It's a little mysterious. I want to talk about why that's important. If you look out in industry, you're not going to find a test receiver today that I'm aware of that natively goes above 40 or 44 gigahertz. I'm not speaking about Roden Schwartz specifically. I'm talking about any receiver manufacturer, to keep this as general as possible. But that doesn't mean you can't make measurements beyond 44 gigahertz. The secret to do so is the use of something called an harmonic mixer. Basically, you have an LO and IF connection on the front of the receiver that you can connect one of these little doodads you see on the slide over to the right here. You can connect that to the front end of the receiver, and these allow you to actually go up to 500 gigahertz, which gives you plenty of overhead beyond the 200 gigahertz the FCC requires. This is great because, as you learned a few slides ago, you can support use cases like what we saw from FCC compliance that requires up to the 5th order harmonic or 200 gigahertz, whichever's lower. Certainly 3GPP compliance test, which was a little less stringent, up to the 2nd order harmonic. And then at the beginning of this section, we talked about radar testing, both aerospace and defense and automotive, 77 to 300 gigahertz. You still have plenty of room to grow as far as that goes. And then there's other applications, of course. This is not an exhaustive list. But if you're analyzing for interferers, people are getting very creative, as we'll talk about later, getting into these higher and higher frequencies. You really want to be able to go see all of that. And kind of the secret weapon to go do that is this harmonic mixer. All right, then. So that's the first trend. Certainly, like I mentioned, I think everyone's heard of 5G. There is a fair amount of things we need to be concerned about from an EMC perspective. But I also want to touch on the standards themselves and how they're evolving. So I think I mentioned quickly before that there's been a lot of action on the military and government side. This slide, of course, focuses on the TEMPEST standard. The 0160 is more for like airborne aircraft and so on. And then your classic MIL standard 461. Another note I want to say before I kind of go into the details of what's shown here is that the majority of automotive standards don't currently go above 6 gigahertz today. And so for a presentation talking about challenges beyond 40 gigahertz, this might seem like a moot point, but the reality is there are examples of automotive standards out there that exist. There's in fact an old Fiat standard that goes up to 18 gigahertz that was over a decade ago when that first came out. And so I think across the board, whatever industry you might be from, all eyes are kind of looking toward growing into the greenfield of higher and higher frequencies. So even though automotive seems to be lagging behind as far as getting higher and higher in frequency, I think the reality is this is coming eventually. And a lot of things typically do come out of the military and government side into other industries. Okay, so what is new? What is evolving in that area? So if anyone has heard of TEMPEST, we're going to talk about that a little bit. Basically, what you're doing is looking for compromising emanations or emissions. So it's one thing to actually find energy that isn't supposed to be at a certain frequency, but it's a whole other thing to actually do something with it. You might want to demodulate that into a signal you might understand. Think about picking off and video rastering someone's screen that might have classified information on it and so on. There's actually a classified standard made by NATO. It's called SDIP 27 that this rather small community tests against that is looking to drive their frequency requirements up to 40 gigahertz. Currently today, their standard that has been published goes up to 10 gigahertz. But like I said, they are looking to go about 4 times higher than that in light of other things going on. DO160 is, again, kind of an airborne type standard here. It's also under development. because of the pandemic, similar to the ANSI C63 committee that Roden Schwartz and myself are a part of, DO160's committee has not met very often either. But the last time I touched base with someone that sits on that committee, they were saying that there is discussion of emissions requirements that goes up to 18 and 40 gigahertz and beyond. So again, it's one of these cases where it's not actually written into the standard yet, but they're certainly considering it, and we'll probably see this in the near future. As a related side note, there is heavy discussion about accepting FFT-based receivers into the standard. And I mention this because those FFT-based receivers are accepted by MIL Standard 461, which typically what you'll find is some of these committees follow what each other are doing, and this is one of those cases. And last but not least, we're going to talk about MIL Standard 461 in a little bit more depth here. There's been more discussion about including requirements around something called automated visual inspection. Right now, they're looking at coming out with revision H. So a little more detail there. If you look at the history of MIL Standard 461, if you study the table on the right and do some quick mental math, you'll see that there's a new major revision released approximately every 6 to 8 years or so. So when revision G came out in 2015, if my math is good here, we're about 6 years since that got released already. So honestly, if it wasn't for the pandemic, I wouldn't be surprised if revision H draft was close to publication now this year, but I don't think that's going to happen, especially since there's only a couple months left in the year. But hopefully in the next 1 to 2 years, this is going to come down the pipe. What this means is that any new program starting 2015 or later must use revision G or later. And so whenever H comes out, the same logic will apply. But the thing I want to talk about here, this is where that comment I made earlier about CU106 comes from, coming up to 100 gigahertz. It would actually be outlined in this revision H. And we actually know a few people that are on this committee as well. One of the things they're looking at building into this, not only the higher frequency component, but also doing what's called visual inspection requirements. And so if you're not too familiar with visual inspection or automated visual inspection at that, I wanted to quickly introduce what this is all about so we all have an idea of what's coming. So just trying to have a little bit of fun with it here as I introduce the concepts. This is of course a Where's Waldo, so you can see if you can find him before I'm finished with the slide. But the idea behind a visual inspection is that oftentimes in an EMC situation, you're going to go put a device under test in a chamber, and you're going to have a human sit outside looking at a computer screen to see if that device under test exhibits some sort of odd behavior that it shouldn't. If it happens to be a vehicle, for example, you might have a shielded camera in the chamber staring at, say, a vehicle dashboard. You know, does it say it's going 100 miles an hour when it isn't? It might be something due to a susceptibility issue. And so there's software and solutions out there that can look at this and quote unquote stare at your device under test so that a human doesn't have to do it. And that's what we mean by automated. You can set these regions of interest. You know, if I'm looking for Waldo, I'm going to reveal where he is. A camera can pick up on these smaller details a lot quicker than you can, and it can look at a lot of different things and focus on 30 or more items at once. Unlike humans, we have a hard time multitasking and doing anything more than like 2 or 3 things at a time. That's kind of the general idea. I had some fun with it with Waldo on the last slide. I'll bring it kind of down into the EMC world now. Like I was mentioning, you might take a device or equipment under test, like a dashboard, into an EMC chamber. You have a camera and antenna, and you're doing a susceptibility test. As I mentioned, if you do this manually with a human, you basically have a pair of eyes staring at a screen. You hope they don't blink. You hope they don't get bored. You hope that they don't have to get up and go to the bathroom or take a phone call. And for a split second, something happens that shouldn't. That kind of makes us error prone. That's the human dilemma. And so if we get fatigued easily and we might miss something, it's much easier to rely on an automated approach powered by a computer with some smart software. And so what do solutions look like for this? As I mentioned, you typically have a camera, you have a computer, you can set these what are called regions of interest. I'm going to show an actual example here in just a moment. You can look for things like color changes, you can look for flashing lights, you can look for objects passing through a certain space or leaving a certain space. You can do optical character recognition if you want to automatically recognize that something is displaying error, for example. You could leave something running overnight and say an error occurred. You could actually log how many times you viewed the error pop up. And as you can see in this event list here, you can keep a log of the date, the time, and how many times the ROI, the region of interest, was triggered. Imagine having a human do that 24 hours straight. It's just no comparison. All right, so some people like myself are see it and believe it type. So this is a vehicle dashboard using an automated visual inspection solution. All these little boxes you see set up like on the turn indicators and some of the idiot lights here, as I like to call them, those are regions of interest. A lot of these are looking for a light to turn on or perhaps a light to turn off. In the case of the blinkers, we're looking at flashing lights. The tachometer here, you can see the analog indicator is looking for the needle to pass through. And then object in, object out is really looking at a pixel by pixel comparison to see if something changes on that screen. And each one of these, I believe this video, I can restart it if need be. I think it starts over on its own, yeah. If the outline is green, that basically means the event has not occurred. If it turns red, that means that the event is actively occurring. And if it turns yellow, it means that some time has passed since the event occurred, but it's not currently occurring. So that's a good way. If something happens just for a split second and you walked away for 20 minutes, you know within the last 20 minutes, something did occur. This can be extremely time saving, especially from an EMC design perspective, because if some unwanted event happened because of a susceptibility test, you know that something needs to be addressed and you won't be surprised when it comes to full compliance time. Again, that's something that they're looking at, including some requirements around in revision H, and who knows where other parts in the industry that may go. Good. So standards are evolving. We talked about 5G. Let's move on to some cybersecurity concerns. This slide is getting a little bit dated, I suppose, but it was still just about a month and a half ago. President Biden came out, and I thought he gave a very interesting quote that kind of sets up the discussion here. Basically, if I was to paraphrase what you see on the slide here, he's basically saying that if we go to war again with like a major power, you know, whatever, he thinks it's going to be a consequence of a cyber breach of great consequence, kind of right in the middle of that whole thing. And this is true. As we kind of look in industry, I'm sure everyone's aware of big companies like Target getting hacked, and there's just a lot of different concerns that are related to cybersecurity. And one thing in the EMC world I mentioned earlier is TEMPEST testing. You know, the idea of it's not enough to know that there's energy at a place it shouldn't be. It's I actually want to do something potentially nefarious with that emission. And so if you go look at this, if you haven't heard of TEMPEST and you want to research what it's really all about, it's actually quite fascinating, because I had to do this not too long ago. The first answer you're going to find is officially TEMPEST does not stand for anything. And I think this is the most true from the experts that I've talked to. When this all started, this was kind of a code name. That's why it's kind of in all caps, which could also suggest an acronym. And you can go find some really, really creative proposals for what TEMPEST actually stands for. This was my favorite one, the tiny electromagnetic particles emitting secret things. As wonderful as that is definitely not the answer. But the most common one, which again, there's some debate as to whether or not TEMPEST actually stands for anything. This one's a pretty good definition that at least captures the spirit of what this community is about. Telecommunications, electronics material protected from emanating spurious transmissions. If you can say that 10 times fast in 10 seconds, I think you should win something personally. But anyway, the point is, TEMPEST is all about these compromising emanations, as I've been mentioning. So there is kind of an art and science to this. It reminds me a lot of interference hunting, if anyone has ever dealt with that particular use case over in the cellular world. But basically, you're looking for something, you're looking for unknown signals at unknown frequencies, just like you are in normal EMC emissions type scenarios. But like that last point says, it's more than just finding the signal like you would in a classic emissions case. It's about doing something with it, potentially demodulating the signal and then determining if something classified is falling into the wrong hands. In this community, there are several test challenges that must be considered. And this, again, we go back to the last section about the standards evolving. These guys are looking at going up to at least 40 gigahertz. That brings about the same type challenges that we talked about in the first section with 5G. You got to make sure that your test equipment can handle the dynamic range required to perform a TEMPEST test. They call that DSS, Detection System Sensitivity. An example of that measurement is shown on the right-hand side of this slide. And then there's other test challenges, like if you want to do something with the signal or the emission that you might find, one thing you can try to do is a use case that's been around for several years called video rastering. You can imagine walking around the Pentagon and someone has classified information on their computer screen. If that computer screen is not shielded correctly, you could actually use an antenna to point at that screen, pick up an emission, and do some fancy trickeration with it. Halloween time, I had to. You could do some trickeration with it and actually recreate what's on that computer screen and say you're a spy from another country. Now, without even touching or even potentially being in the same room with somebody, you've just acquired classified information that doesn't belong to you, which could be a big, big problem. And last but not least, another challenge is signal analysis and recording. This is kind of a nod to what we'll talk about in the last section, which is IQ. Before we get there, a few more details about what I was talking about. I think this cartoon was really capturing the spirit of what I was talking about. You've got a bad guy here with the antenna outside of a room trying to pick off what this guy's working on his computer. And if you're not familiar with video rastering, there's a definition here. It's really a dot matrix data structure. So every computer screen is made of several pixels that are quite literally rastered into rows. And these PC monitors, it could be a video screen, whatever, they emit electromagnetic radiation if they are not sealed properly. Rastering is actually the process of capturing that content over the air and then using it to kind of, again, I call trickeration. That's like my favorite word. But if you look at this bottom right-hand screenshot, this is a real example. This was an antenna pointed at a computer screen roughly 6 feet away. And you can see just how clearly you can read the letters on the screen. This is just a classic, the quick brown fox jumps over the lazy dog, just a sample message, but there's letters at all different sizes and you can see black lines. It's actually a pretty clear display. When you think about it in terms of Big Brother and stuff like that, it's pretty scary that we can do this kind of stuff. And as the bad guys get more and more creative, we'll talk about in the last section, this is something that a lot more companies out there, especially of course in the government and three-letter agency side, this is becoming a very popular application. So if you find yourself in an area that you might be interested in, making sure that you don't have any cybersecurity concerns, there are several solutions that exist. There are specialized test receivers. There are antennas out there that are active and passive. They cover very wide frequency ranges. Of course, we're talking about challenges beyond 40 gigahertz today. We're not just talking about simple little measurements down in 6 gigahertz or below anymore. We're talking very, very wide, which means there could be a lot of antenna changing. Even antenna design is changing such that you can do this a little easier without having to change as often. And then I just included a test system here. I mentioned the DSS measurement on the last slide to make sure that you have enough dynamic range to perform the measurement. That requires quite a few different pieces of equipment aside from just a receiver and an antenna. There are customized solutions out there that make this much easier to have everything in one place where you need it, and certainly software to power it. All right, and that brings me to the fourth and final industry trend, which is IQ, record and replay. So if you don't know exactly what this is all about, I'd like to quickly introduce the idea. So going back to college days, right? Every signal out there has an in-phase and quadrature component to it, affectionately known as INQ. You can see how that's mapped over here. This occurs down in baseband, and there are solutions out there that can record this baseband. There's a good block diagram at the bottom of the slide down here that kind of shows the whole idea. If you're an automotive customer, for example, trying to test how a module might be able to do out in the real world, it might be advantageous to go out in the real world and capture signals, the RF spectrum, use something like a spectrum analyzer to record all those signals happening over the air. And then once you've recorded those signals, you could actually replay them through a signal generator to kind of stress test whatever module or electronic piece you're trying to stress test. That's the whole idea here. And the longer you can record, it means the more signals you can replay for a longer period of time, the better your stress test is going to be. This is versus what a lot of people do. They try to simulate signals that aren't necessarily real world, where you have multipath and intermodulation and all kinds of interesting RF effects. Nothing beats the real thing. So more and more people are waking up to this as the test setups are getting more and more complex out there. They want to get as close to the real thing as possible when they stress test. So I mentioned that specific example on purpose. A lot of you are right in the backyard of this. Hopefully you've heard of M-City, but this is like my favorite test facility to talk about. Some of the testing challenges in this area have to do with coexistence and spectrum refarming. And that's the whole idea. You would drive around M-City where they have a lot of V2X stuff set up. They've got special stoplights and all kinds of signals going around. This is like a simulated city. Highly recommend going and checking this out if you haven't already. But you're really trying to determine, how do these signals interact with each other, and can I stress test my device, and could higher frequencies work better? Because everything has been crowded down at 6 gigahertz or below. A lot of people are getting up to 18 gigahertz, I would say, is another common breakpoint. But we're talking about going even higher as we kind of push the limits of how much data we can push in a certain amount of bandwidth and how far we can travel at the millimeter wave frequencies. Going over to the aerospace and defense side for a second, this is actually one of my favorite examples of why IQ testing is so important. You can see on the right-hand side of the slide, you find this IED, improved explosive device. It's using a cell phone. It's actually the detonator. So if you go back about 10 to 15 years ago, when we didn't have anything even close to millimeter wave frequencies, the bad guys would go out there and get a commercial Nokia phone. That thing's probably considered a fossil at this point, but I remember them. They would go out and buy one of these, and if you made a phone call, that signal would traverse over a good amount of distance and find a bomb and detonate it. So back when we had a big problem with that, the government and other customers got really smart, and they said, you know what? We'll just go higher in frequency, and then that's not going to work anymore. Well, now that we're into the 5G world and FR2 goes up to 54 gigahertz and beyond, now we have commercially available modules for 5G. So now if you want to take the same strategy, if you will, and go even higher in frequency, well, you see the point. Now it's getting harder and harder and harder because we're getting up there quite a bit. How do you stay safe? That is something that a lot of people have to think about. Some more testing challenges. If you've never seen what a jammer looks like, I provided a good example here of one that actually does 5G and GPS. This is something that people like to do. Back in my prior role with mobile network tests, there's so many stories we could talk about, but one of my favorites has to deal with jammers. You get like restaurant owners. We had one time that decided that everyone needed to have quality time. If a family came to his restaurant, the kids shouldn't be on their phones, and they should just be able to look at each other in the face and have quality conversation. Love the idea, can get behind it. However, it's highly illegal, because if someone has a heart attack and they can't call 911, you got a big liability issue on your hand, and that's just not a good thing. So as we get up higher and higher in frequency, of course, there's bad guys out there that are trying to develop jammers to clog up these things. And that same argument applies to GPS. Think about truck drivers that they don't want their boss to know where they were on a 2-hour lunch period. So finding jammers is one thing, but also the fact that we have to keep in mind that these things exist is also a testing challenge in itself. And last but not least, I put TEMPEST here. We just talked about it in the last section, characterizing those compromising emanations. Why this is interesting to those guys is, okay, I found a signal, just like I would in classic EMC emissions cases. I'm going to do something with that signal. I might raster it, or I might audio demodulate it and listen to something. But if I really want to get interesting with it, I could record its baseband IQ, and I could replay it back again and again and again and see if I could stress test it on something else, or I could keep a signal library to look for patterns. You know, if there's someone out there doing something funky, maybe they have some kind of signature in the RF spectrum. There's so many different ways to look at this, but you're not just characterizing the emanation, you're actually recording it, that you can look at it again at a later time to see if you can learn more about it. All right, and along those lines, the longer you can record, the better. Another testing challenge here is the longer you want to record, the wider the bandwidth of the signal you might find, the more hard drive storage space is going to be required. So this is a good table set up here that kind of gives you an overview of just how much hard drive space you're going to need. These days, something above 3 terabytes is actually not enough in many cases. Some of the solutions out there have as much as 15 terabytes available. And if you're recording a signal that has a gigahertz bandwidth, that gets you just over an hour of recording time, which in the grand scheme of things is a long time. But of course, as you see in the table here, the lower the bandwidth, the longer you can record, which is ideal, just to give you a feel for how that goes. All right, so that's the recording piece. Of course, you also want to be able to analyze the signals and replay the signals, as we talked about earlier. In the analysis stage, you might want to look at the constellation diagram. There's some good VSA software out there, vector signal analysis, that can do all kinds of spooky things, keeping in our little theme here. And then replaying the signals involves a signal generator. You have to have an arbitrary generator there. You never know what you might record in the real world. So you put that in there. Of course, you need an antenna to output the signal back into the lab environment or wherever you might be to replay it. Down in the bottom right-hand corner of the slide there, I included a example solution again that kind of combines all these things together. You can do certainly the recording and replay piece, but you can even do the analysis on board with the system in one place, which is pretty cool. Solutions are getting very creative today. Okay, so I've reached the end of the presentation. I'll wrap it up real quick and look for some questions here. But basically what we talked about today is, of course, EMC testing challenges beyond 40 gigahertz. What we've learned is that the industry requirements are going up to 300 gigahertz and beyond. Now, we talked about some of the emerging applications, including 5G radiated spurious emissions. We briefly touched on radar testing. We talked a lot about TEMPEST, and certainly more use cases and testing challenges that pose some pretty scary things. And that's the real world that we all live in. Military Air Force 301 Revision H is underway. If it wasn't for the pandemic, I think there's a good chance it would be here, but keep an eye out for that to come out maybe in the next 1 to 2 years, and we'll see how that spreads out into other industries. And it may include visual inspection, which has a lot of cool things that may be able to help in some of the challenges we saw in that area. All right, so with that, I want to thank you all again for giving me the opportunity to speak with you. I really do look forward to next year when maybe we'll be doing this face-to-face. I hope you learned something interesting tonight. And if you have any questions, let's just go ahead and check the chat to see what we've got.
Hey, thank you so much, Jeremy. Let me get my camera back on here.
All right.
So yeah, there is a number of comments in the chat window. I don't see a specific question yet. So if anybody has a specific question, please open your mic and camera if you would, and then go ahead and ask your question to Jeremy at this time.
I have my hand raised.
Okay, I see a hand raised. Go ahead, Michael.
Okay, on the last set of slides, you're talking about, the signal playback capabilities. One thing you have to keep in mind, it's not just enough to have an arbitrary signal generator, but it has to be able to support that high-speed streaming. Like, I'll give an example, and not to pick on you guys, because we got a lot of your stuff and we like it, but we have an SMW 200A, and we've synthesized DAB signals. But because it can only replay what's on, it'll only replay what's in ARB memory, which we only have like 256 megabytes worth. That limits us to like a 30-second DAB playback segment. So if you need longer, then your signal generator has to support streaming from some, from the storage media, from your terabyte hard drives and such.
Yep.
Unless I'm doing something wrong and you can give me a hint.
No, thanks for bringing it up. That is a good point. In the presentations like this, I tend to oversimplify for the sake of time, but sample rates and the capability of your test equipment is certainly a factor. And it sounds like you've run into that. And as signals get more and more complicated, I think test equipment has to be able to keep up, and it's something to keep an eye on. So thank you for sharing your experience.
Okay, thank you, Michael. Next question, please.
Yeah, I saw Malcolm just made a comment. Yes, Oktoberfest, the real deal, was canceled in Germany this year. So we are lockstep with what they're doing there as well, if that makes anyone feel better.
Okay. That's too bad.
It is. I know folks over there are very much looking forward to things getting back to normal too. That is a very fun place to be.
Okay, any more questions from anybody before we move on?
I got more.
Okay, go ahead.
So as far as this testing stuff goes, I mean, I think maybe I'm wrong, but I think a lot of the automotive grade, large anechoic chambers don't go past like 6 gigahertz or maybe 10 gigahertz. So what do you think is going to happen there?
Well, I'm going to say my piece. I know there's other Roden Schwartz people on here. They can feel free to chime in as well. As we talk about getting higher and higher in frequency, we know that these signals attenuate very quickly. And so a lot of times you can actually have an open air type test, and you don't have to be worried about a lot of things bouncing around because they'll just attenuate by the time you even get any further. And so in many ways, I don't know how much more measurement integrity, if you will, you could have when you get up to these much higher frequencies. Does anyone else have a take on that?
So Jeremy, you're recommending like open area test site for this?
Yeah, like that's one alternative that you could consider for sure.
Okay.
But then it sounds like the existing anechoic chambers might be adequate, even if the absorbers don't work. They don't work well at those high frequencies. The path losses are so great that it kind of doesn't matter.
Yes, this is also true. I know for a fact that the guys in the TEMPEST community, a lot of those guys don't perform measurements in a chamber. Some of that is because of what they're doing, but some of that is also because of just the signals they're looking at, which is part of the discussion we're having now.
Well, the guys doing TEMPEST don't care. They just want to be able to listen to the emanations coming from whatever and then try to make sense of them.
Yep, that's also true.
Let me chime in here. It's Achim from Roden Schwartz. Most of the chambers and most absorbers, even if they are specified up to, let's say, 20 gigahertz or 40 gigahertz, most absorbers actually work way into the, let's say, 80, 90, 100 gigahertz range. The issue with most of those absorbers is that actually I don't even know of any of the absorber manufacturers that has capabilities to even test those absorbers beyond 40 gigahertz. But I know from some that actually have performed, let's say, testing. Most absorbers work, let's say, pretty well, even if you go higher in frequency. So I wouldn't see a big issue when it comes to the performance of the anechoic chamber itself.
Thank you, Michael.
Interesting.
Welcome.
All right, I yield the floor until I can think of another question.
Okay, go. Okay, go ahead, Michael.
Oh, actually,
Nothing more?
no, not right at the moment. Something
Okay.
will come to mind. It's unfortunate. I got in here a little late because it took me a little while to get home from work, but
Okay.
and I missed some of the early stuff. I assume the slides will be available.
Yeah, we'll have the slides and video available afterwards. So not to hold everybody up, if you think of your question, maybe we can do it afterwards. So let's move on to the drawing at this time. And we're going to turn this over to Eric Fox. Eric, unmute yourself there.
No, that would help. Hey, everybody. So what we showed in the beginning, so what we have are 6 of these large 1 liter, these are where the waitress and in Munich would have, carrying 8 of these things. These Oktoberfest mugs. So I don't know who would actually need 6 1 liter mugs for themselves. So I think what we decided is going to break it up into 6 individual drawings. I've got my handy little Detroit Tigers cap here with everybody's name in there. And if you could just say present, or somehow let us know, because we're got to be present to win. So as I pull it and say the name, just let us know that you're here, and I'll hook up with you afterward and figure out how to get the mug to you. All right, first name we have is Sean Shadroke. Do we have Sean?
Yes, I'm right here. Wow.
Okay, mug coming your way.
Thank you.
Congratulations. All right, number 2. Jim Woodyard. Pretty
I'm
sure.
here.
Yep, I'll say I'm pretty sure I saw you earlier. All right. Third one, we have Elizabeth McKenna.
I'm here.
Okay. Hope you like beer. There's a lot that goes in that. All right, we have John Suriano.
Yeah, I'm here.
Yeah, I thought I saw your name. Okay. Hakan Davidson.
I did not see him tonight, Regis. I did not see him.
Our 5th one. It took a while to find someone who wasn't on. That's good. All right. Barry Stouts. Big mug coming your way.
Yes, I'm here.
And the 6th and final one, we have Pradeep Sagdeho.
Spell the last name.
Sagdeo.
Yeah, I don't show him.
Okay. Go back into the hat here. Bill Demaray.
I didn't see Bill,
I
but
didn't see Bill either.
no.
I don't see Bill on there either. Bill works for next year.
Yeah.
Correct. David Evans.
Oh, yes, I'm here.
Oh,
Okay, I was just gonna say, man, this 6th one's hard to give away.
right.
All right, so there's our
Okay.
6 mugs. So I'll reach out to you guys via email and figure out how to get them to you. And congratulations.
Perfect. Yeah. Congratulations, everybody.